Well, in this chapter there are 8 questions, and here are the answers. First one, it's talking about central maximum, the width of the central maximum, and to find that, the idea is that you just find the width of the first minimum, because at the edge of the central maximum on both sides you have the first order minimum. Okay, the width of the central maximum is twice the distance from the center to the first minimum, or from the central maximum to the first minimum, and sine theta is lambda by d from which you can find theta. That is the wavelength, and here caps d is the width of the slit. You get that? Then if the distance is y1, then y1 is L tan theta, or tan theta 1. So okay, you can change the angle now into a distance. L is 5 meters. So now take twice that and you get the answer, which is the width of the central maximum. In the second one, the wavelength is given, and the diffraction maximum is 6 centimeter wide on a screen, 2.2 meter away. What will be the width of the diffraction maximum for light of nether wavelength? So it's a comparison question here, and I've already shown that y1 is L tan theta 1, and it will be half. Okay, y1 will be half of the width of the central maximum. So you can find theta. So 0.781 degrees, and sine theta 1 is lambda by d. So we can use the first information to find the width of the slit, and then use it in the second case. So once you get d, once you get d, you have to continue. You have to use that to find the width. In which case you would go y1 or y2 in fact is equal to L tan theta 2 and for that you'll have to find theta 2 using sine theta 2 is equal to lambda 2 by d. So lambda 2 is given as 460 nanometers, so you go 460 times 10 to the negative 9 divided by the distance of this, so which is 42,537. I have not calculated this, and once you get theta 2, you put that theta 2 back into this equation, you know the distance, you find y2, and then double y2. So 2 times y2 would give you the final answer. In question 3, it's about resolution. Now, if those are the two stars and the distance between them is L, and the distance from the Earth is R, then we know for a circular aperture, theta is 1.22 lambda by d. Whenever you have theta, it should be in radians, remember that. In this case, since we substituted as 1.22 lambda by d, it doesn't make a difference. Now, that is light years. Now, this quantity is light years converted into meters. So that's the distance traveled by light in 1 year in meters. Then you have the wavelength. And so you find that the distance between the stars is 1.5 times 10 to the 11 meter. In the fourth one, it's about a grating, and for a grating, you can write it as d sine theta is m lambda, but n is 1 by d. Remember, n is the number of lines in 1 meter, and d is the width of one slit. Now, it's always good to have it in that format. Remember it that way. Sine theta is nm lambda. Show me again the subject, because you're asked to find how many lines. But remember, you're getting this as number of lines in 1 meter. Okay, because I took that as 650 times, actually it should be 650 times 10 to the negative 9 if it was in meters. But since I'm just using 10 to the negative 7, it's in centimeters. That is why the answer says 1300 lines per centimeter. In the fifth question, again, you have to find the angular spread in the second order spectrum between red light and blue light. So which means you have to individually calculate the theta for each one. So that's the formula for theta that you get when you rearrange. And then substitute the values of lambda. For both, m is equal to 2 because it says second order spectrum. So you get theta 1, and that is for blue light, and then you find the same for red. And now take the difference, and you get the angular spread. (24 degrees). In the sixth question, the two polarizers oriented at 36 degrees. First angle, because light is polarized at 18 degrees, so the first angle between light and the first polarizer is 18 degrees, but the angle between polarized light and the second polarizer is 36 degrees. So use the formula, which is for intensity, which is I1 is I naught cos squared 18, first case, and then use that to find I2. So you get it as 0.592 I naught, which is 59.2% of the initial intensity. Seventh one talks about unpolarized light passing through 6 polarized sheets, each making 45 degrees. That's the formula for intensity. The first one always reduces the intensity by half. And so from the second to the sixth reduces the intensity by half. In this case, because it's 45, and cos squared 45 is 1 by 2. And sheet 1 always reduces it by 1/2, because it only transmits one component and restricts the other. Therefore now, since each one reduces it by 1/2, and that's 6 times, so it's raised to 6. Therefore, the final intensity is only 1.6% of the initial. In the last question, light is incident at polarizing angle. So now you see the reflected ray and the refracted ray, and you have to prove that the angle between them is 90 degrees. That is, if that's theta I, that's also theta I, and that is theta R. N1 and N2, refractive indices, Snell's law, N1 sine theta I is equal to N2 sine theta R. And then use Brewster's law, which says tan theta P is equal to N2 by N1. And theta P in this case is theta I. So you know that tan is written as sine by cos, so take the cos to the other side, rearrange, you will get N1 sine theta 1 is equal to N2 cos theta. N1 sine theta I is equal to N2 cos theta I. Now look at equations 1 and 2. The left hand sides are equal, therefore the right hand sides must be equal. The N2's cancel out, and the cos on the right side can be written as sine 90 minus that angle, because sine 90 minus an angle is cos of the angle. Now you rearrange, you see that theta I plus theta R is 90 degrees. The total angle is 180, and if theta I plus theta R is already 90, if those two add up to 90, then surely the remaining angle is 90 degrees. Therefore, the reflected and refracted beams are perpendicular to each other. Thank you.